Welcome to our latest video on Group 3 electronic configurations, oxidation states and electron deficiency. This video is suitable for A-level students. By the end of this video lesson, you should know the elements that make up Group 3 and be able to explain the oxidation states that occur in the group. You should also understand the electron deficient nature of Group 3 systems and how this is overcome in terms of the formation of dimers and donor-acceptor compounds. And finally, you should understand how chemists make use of the electron deficient nature of aluminium chloride in terms of ionic liquids and their use as catalysts. Now, the 5 elements in Group 3 are boron, aluminium, gallium, indium and thallium. And these 5 elements are part of the p block in the periodic table, and this is because their outer electrons are in a p orbital. Now, each element in Group 3 has a characteristic s2p1 electron arrangement. And the 2 most common elements in Group 3 are boron and aluminium. And it's these 2 elements that you need to know about for the exam. Now, these elements have very different physical properties, as one is a non-metal and the other is a metal. Now, although aluminium is a metal, it forms small, highly charged positive ions, and as a result, some of its compounds are covalent due to polarization of electrons. Now, compounds of aluminium and compounds of boron do have some similarities, and we're going to look at these during this lesson. Now, to get you started with Group 3, we're going to attempt some practice questions, and in these practice questions, we're going to look at electron arrangement and some of the uses of these elements. So here's our first 2 practice questions. Read through the questions, pause the video, have a go at them, and then we'll go for the answers. So question 1 is asking you to write down the electron configurations of the first 3 members of this group. So boron has an atomic number of 5. That means it has 5 protons and 5 electrons. So its electron arrangement will be 1s2, 2s2, 2p1. Now, aluminium has an atomic number of 13. 13 protons, 13 electrons. So its electron arrangement will be 1s2, 2s2, 2p6, 3s2, 3p1. Now, gallium has an atomic number of 31, so it has 31 protons, 31 electrons, and the electron arrangement will be 1s2, 2s2, 2p6, 3s2, 3p6, and then the 4s fills before the 3d, so it's 4s2 here, then it's 3d10, 4p1. 1 mark for each correct electron configuration. Now, for question 2, you're asked to explain why Group 3 elements are classed as p-block elements. Now, this is because their outer electrons are in p orbitals. Notice that the last electron that we placed in an orbital was in a p orbital. Now, that's why they're classed as p-block elements, and if you got that, there's 1 mark. So here's our next set of practice questions. Once again, read through the questions, pause the video, have a go at them, then we'll go for the answers. So for question 3, you have to match the description to the Group 3 element, and there's 1 mark for each correct match here. So A states, this highly reactive element is the most abundant metal in the world and is found in ores such as bauxite. Well, this element is aluminium, 1 mark if you said that. Now for B, this non-metal element is found as borax in alkaline lakes in California and boric acid in the hot springs of Tuscany. Well, the element is boron, 1 mark for that. Now for C, it says this soft grey metal is often used in conjunction with elements such as sulfur and selenium to make low melting glass. It is highly toxic and was once used in rat poison and insecticide. Its salts now find uses in photographic films. The element is thallium. 1 mark for that. So here's the rest of question 3. So read through the question, pause the video, have a go at it, and then we'll go for the answers. So once again, for question 3, you have to match the description to the group 3 element. So for D, this soft silvery metal is used in the semiconductor industry in the manufacture of diodes and transistors. It is sourced from compounds that are present in trace amounts in zinc ores and bauxite. Well, this element is gallium. 1 mark for that. Now for question E, it says this soft silvery white metal forms compounds that can be used in LEDs and semiconductors. The radioactive 111 isotope of this element is used in medicine as a radio tracer to follow the movement of labelled proteins and white blood cells. Well, this element is indium. 1 mark if you said that. So now we've learnt about the electronic configurations of group 3 elements and their uses. We're now going to look at the oxidation states of these elements and the inert pair effect. Now, all the elements in group 3 form compounds in which they exist in an oxidation state of +3. Now, the stability of compounds with elements in this oxidation state decreases on descending the group. The +1 oxidation state arises from what is known as the inert pair effect, and this is something that we've discussed previously when studying group 4. Now, this is when 2 of the 3 bonding electrons become less available for bonding down the group. So the +1 oxidation state becomes more stable down group 3 due to the inert pair effect. So if we look at this table, we can see the boron is at the top of the group and has an oxidation state of +3 only. Aluminium also only has an oxidation state of +3. Gallium has an oxidation state of +3 and +1, but +3 is the most stable. Indium has an oxidation state of +3 and +1, but it's the +1 oxidation state that's more stable. And thallium, once again, has an oxidation state of +3 and +1, but it's the +1 oxidation state that is the most stable. So now let's look a little more closely at what we mean by the inert pair effect. Now the electron arrangement of boron is 1s2, 2s2, 2p1. Now in the +3 oxidation state, boron uses all its 2s and 2p electrons in bonding. And you can see I put a red box around these electrons to show that it's these electrons that are used when boron bonds to another atom. Now thallium has an electron arrangement which ends in 6s2, 6p1. And in thallium's more stable +1 oxidation state, thallium only uses its 6p electron in bonding. The two 6s electrons are not used in bonding and are referred to as the inert pair. And I've underlined these electrons here on this slide. Now the inert pair effect is the tendency of the s2 electrons in an atom to remain paired and not to be used in bonding, and this causes an oxidation state which is too lower than the element's highest oxidation state. So now let's test your understanding of oxidation states and the inert pair effect with a practice question. So read through this question, pause the video, have a go at it, and then we'll go for the answers. So this first question is asking you to list the most stable oxidation states for the following elements. So for this question, you have to realize that if the element is at the top of the group, it will use all its outer shell electrons for bonding. And if it's towards the bottom of the group, there'll be a tendency for the s2 electrons not to be used in bonding. So therefore, an oxidation state will be exhibited which is 2 less than the maximum oxidation state. So question 1a is asking for the most stable oxidation state of lead. Now lead is the bottom element in group 4, so the inert pair effect gets stronger down the group, so therefore the most stable oxidation state will be +2. Now for question B, thallium has a most stable oxidation state of +1, and this is because it's in group 3 and it's at the bottom of group 3, and the inert pair effect becomes stronger down the group. Now nitrogen is at the top of group 5, so its most stable oxidation state will be +5. Aluminium is towards the top of group 3, so its most stable oxidation state will be +3. Now bismuth is at the bottom of group 5, so therefore its most stable oxidation state will be +3 due to the inert pair effect becoming stronger down the group. And germanium is in the middle of group 4, so its most stable oxidation state is +4. 1 mark for each correct stable oxidation state. So now that we've looked at the oxidation states of group 3, we're going to turn our attention to the electron deficiency that exists for compounds of boron and aluminium. Now compounds of boron and aluminium are often described as being electron deficient because in these compounds the boron and aluminium atoms do not end up with a full outer shell of electrons, i.e. they don't have the normal stable octet. So to illustrate this, I'm going to put in the electrons here in the dot and cross diagram that are being shared between first the boron and the chlorine atoms. And you can see that the boron only has a share of 6 electrons here, 3 pairs of electrons. If I do the same with aluminium chloride and I put the electrons in that are being shared between the aluminium and the chlorine, once again it only has a share of 3 pairs of electrons. It doesn't have the normal stable octet of 8 electrons. And if I once again put this in for BF3, you can see once again boron only has a share of 3 pairs of electrons. So these group 3 compounds are said to be electron deficient, and they only have a share of 3 pairs of electrons, and therefore they will often form coordinate bonds to other atoms and molecules to gain extra electron pairs. They are classed as electron pair acceptors. And if we were studying organic chemistry, we would refer to them as being electrophiles because they'd be electron pair acceptors. But in inorganic chemistry, we refer to them just as being electron pair acceptors. Now, one such compound that is electron deficient is aluminium chloride. Now, aluminium chloride has covalent bonding even though it consists of a metal and a non-metal. And this is due to polarization. The small highly charged positive ion attracts electrons from the large negative ion so strongly that the result is a compound with typical covalent properties and typical covalent character. Now monomeric aluminium chloride, AlCl3, is electron deficient as each aluminium has 3 electrons in its outer shell, whilst each chlorine contributes 1 electron to its valence shell. So it only has a share of 3 pairs of electrons. It doesn't have the normal stable octet. Now, aluminium chloride can achieve a full outer shell if it exists as a dimer, Al2Cl6. And the dimer is formed when 2 AlCl3 molecules link together as a result of the donation of lone pairs of electrons from 2 of the chlorine atoms, 2 dative bonds. Now to illustrate this, I'm first going to draw a dot and cross diagram to show the bonding in monomeric aluminium chloride, AlCl3. And you can see here, if I put in the dots to represent chlorine's electrons and crosses to represent aluminium's electrons, that aluminium only has a share of 3 pairs of electrons. It doesn't have the stable octet. It doesn't have 8 electrons in its outer shell. Now, if I draw the dimer Al2Cl6, you will see that both aluminiums here achieve the stable octet. They achieve full outer shells. And this is done by the 2 chlorines, the bridging chlorines between the 2 aluminiums, forming dative bonds, coordinate bonds to the aluminium. So I'm going to put in dots and crosses to represent aluminium's and chlorine's electrons. So a cross is aluminium's electron and the dot is chlorine's electrons. I'm not going to put in all the electrons for chlorine here. I'm just going to put in the electron pairs that are being shared. And you can see that there are two dative bonds here. One chlorine forms a dative bond to one aluminium, and the other chlorine, the other bridge in chlorine, forms a dative bond to the other aluminium. And that's how both aluminiums achieve full outer shells, stable octets, outer shells with 8 electrons. Now I've chosen to use a double-headed arrow here to represent each dative or coordinate bond. However, you could just use 2 dots to represent the pair of electrons. Now in the example we've just looked at, aluminium chloride was electron deficient and bonded to another aluminium chloride to achieve its stable octet, and it existed as a dimer. However, AlCl3 could have accepted a pair of electrons and formed a dative bond to a different molecule, and we would then form a donor-acceptor compound. Now, an example of this is shown on this slide. BF3 is also described as being an electron deficient molecule, and the lone pair on the nitrogen of an ammonia molecule can be used to overcome this electron deficiency, and a compound is formed involving a coordinate bond. Now the BF3 is classed as an electron pair acceptor, whilst the ammonia is classed as an electron pair donator. Now once again, if we were studying organic chemistry, we would refer to the electron pair acceptor, the BF3, as being an electrophile, and the electron pair donator, the ammonia here, as being a nucleophile. Now if you undertake wider reading, you may come across in some books that BF3 is classed as a Lewis acid, while the ammonia is classed as a Lewis base. Now the terms Lewis acid and Lewis base were introduced in 1938 by the American chemist G.N. Lewis to extend the concept of acids and bases even further than that of Bronsted and Lowry. Now you don't need to know the term Lewis acid and Lewis base. However, you do need to be able to recognize where electron pairs are being donated and electron pairs are being accepted. So we've just seen that group 3 compounds such as BF3, AlCl3 and BCl3 are electron deficient. Now chemists make use of the electron deficiency of group 3 compounds in catalysis and in the development of ionic liquids. For example, in the chlorination of benzene, we use anhydrous aluminium chloride as a catalyst, and this compound is key to the formation of the electrophile, and the reaction here, benzene plus chlorine to form chlorobenzene and hydrogen chloride gas, is an example of an electrophilic substitution reaction, and the electrophile Cl+ is generated using aluminium chloride and using aluminium chloride's property of being electron deficient. Now the fact that AlCl3 is electron deficient and will readily accept a pair of electrons from a chloride ion to form AlCl4- is made use of in the development of ionic liquids. Now chemists know that if we form an ionic compound where there's big differences in the size of the positive ion compared to the negative ion, the attraction in the lattice will not be as strong. Now the attraction of these ions can also be weakened if we have ions that have very different shapes. Now the AlCl4- ion is a large molecular ion and is quite stable, and therefore it is often combined with much smaller positive ions in these ionic liquids. And when there's a big difference between the size of the ions, the attraction is not as strong, and therefore the melting points are a lot lower than typical ionic compounds. And that's why these ionic liquids are liquids at room temperature. Now, ionic liquids with low melting points that contain the chloroaluminate 3 ion, AlCl4 1-, are being developed as clean technology solvents and catalysts for processes such as the polymerization of alkenes. And these ionic liquids are replacing organic compounds because they have a number of advantages. Firstly, they're non-volatile, so they don't evaporate during use. And secondly, they're often easier to separate from catalysts and products than organic compounds. So now we're going to test your understanding of what we've learnt in this video lesson with some practice questions. Here's the first practice question. Read through the question, pause the video, have a go at it, and then we'll go for the answer. So question 1 says the compound AlCl3NH3 contains both covalent and coordinate bonds. Complete the dot and cross diagram for this compound. So the aluminium chloride covalent bonding diagram was drawn for you, and you have to draw ammonia, NH3. You have to have the correct structure for ammonia, and you have to show that it's forming a coordinate bond to the AlCl3. So if you got the correct bonding for NH3 with 5 electrons in the outer shell of nitrogen and it forming 3 covalent bonds to the hydrogens, that gets you 1 mark. And if you then got the correct dative bond or coordinate bond between the nitrogen on the NH3 and the aluminium chloride, you get the 2nd mark. So here's our second practice question. Once again, read through the question, pause the video, have a go at it, and then we'll go for the answers. So question 2 says aluminium chloride AlCl3 can be used to produce compounds including the chloroaluminate 3 ion AlCl4-. And it says draw a dot and cross diagram to show the electron arrangement in the AlCl4- ion. So I'm drawing an atom of aluminium here, and aluminium's got 3 electrons in its outer shell, and I'm forming covalent bonds to chlorines here, and I'm only going to put in the outer electrons for both aluminium and chlorine. So I'm doing a dot and cross diagram here to show the bonding that is present in. First I'm going to draw AlCl3, and that's what I'm putting in the electrons for each chlorine atom here. And you'll notice that chlorine's got 7 electrons in the outer shell, and I'm representing these by dots, and it gains a full outer shell by sharing with one of aluminium's. Now to change this to AlCl4-, I draw a dative bond, and a pair of electrons is coming from a chloride ion here. So the chloride ion has 8 electrons in its outer shell. That's why I'm able to draw this dative bond. And the molecular ion that forms has a 1- charge. So part 2 says give one industrially important use in which the AlCl4- ion is involved. State the role of the ion in this use, and this is a 2-mark question. So you could say the chlorination of benzene, because when you form the AlCl4- ion, a Cl+ ion is produced as an electrophile. So there's 1 mark if you said chlorination of benzene, and 1 mark if you mentioned the production of Cl+ as an electrophile. Now an alternative answer is to say it forms ionic liquids, because AlCl4- is an ion which is often used in the formation of ionic liquids, and it gives these ionic liquids low vapor pressure, it makes them non-volatile, and they do not evaporate in use. So there's 1 mark if you said that. So if you went with the ionic liquid use, you'd get 1 mark for the mention of ionic liquids and 1 mark for the idea of having low vapor pressure or being non-volatile or not evaporating in use. Finally, the use as a catalyst in the polymerization of alkenes was also accepted. 1 mark if you mentioned catalyst, 1 mark if you mention the polymerization of alkenes. So that concludes this video lesson. So after watching this video, you should now know the elements that make up group 3 and be able to explain the oxidation states that occur in the group. You should also understand the electron deficient nature of group 3 systems and how this is overcome in terms of the formation of dimers and donor-acceptor compounds. And finally, you should understand how chemists make use of the electron deficient nature of aluminium chloride in terms of ionic liquids and their use as catalysts. So that concludes this video lesson. So please check out our YouTube channel, Dr. O Chemistry, which has lots of GCSE, AS and A-level videos, and our Twitter site @RadaChemistry.